In this video, we'll work some more problems, and we'll focus on arc length, area, volume, and center of mass. So let's consider the region R bounded by the x-axis, the y-axis, and f of x equals cosine of x. So we can see what that looks like in the yellow region there marked R. So we are going to ask first, what is the perimeter of R? So the perimeter is going to include that segment that goes from the origin up to 1. So that'll be just 1. We'll get that horizontal segment going from the origin to pi over 2. And then the interesting part is we're going to have to find that length of that curve, the cosine curve, from the 0, 1 to the pi over 2, 0. So remember, our arc length is given by an integral from a to b of the square root of 1 plus f prime of x squared dx. So our derivative, f prime of x, is going to be a negative sine x. So that's going to make our arc length be that integral from, we're going from 0 to pi over 2, and that's going to be the square root of 1 plus, and negative sine x quantity squared is going to be sine squared x dx. So I'm going to just do this on our calculator. So I'm going to pause it for a moment. And I'm getting that to be about 4.481. 4.481. So if we take that, and so we add the 1, the pi over 2, and our 4.481, then I'm getting I'm sorry, the first one I jumped to the answer there. That should be 1.190. 1.190. Sorry about that. And that is going to be our final answer. So 1.190 plus the 1 plus the pi over 2, that's going to be the 4.481. Okay. Okay, let's find the area of the surface formed by revolving f of x on the interval from 0 to pi over 2 about the x-axis. So if you remember, we're going to take our curve here, and if we revolve that about the x-axis, then we know that our delta area is 2 pi r, and we're going to have to decide what that radius is. And then the shorthand version is going to be that differential arc length. So in our case, if we are revolving around the x-axis, then that radius is going to be our function. So that's going to be 2 pi times our cosine x, that's the radius, and then we're going to get our square root of 1 plus, and we said that was going to be sine squared x. We will then get the area will be 2 pi, and we'll do that integral going from 0 to pi over 2, and that's going to look like cosine x square. I should have put maybe a delta x in there, and that'll be a 1 plus sine squared x dx. So I'm just going to put this on my calculator, and I'm getting 7.212. Now if we revolve it about the y-axis, then our delta area is again going to be 2 pi r times our differential arc length, which we call ds. So this time, though, the radius, that distance out to that little differential segment there, is going to be just x. And the ds will still be our 1 plus sine squared x, and that'll be a delta x for right now. So that will make our area be 2 pi. This time we'll go still from 0 to pi over 2, and that's going to look like x times the square root of 1 plus sine squared x dx. And I'm going to put this on the calculator also. And on this one, I'm getting 10.074. Okay, I'm going to slide the screen up. Set up, but do not integrate an integral expression that represents the volume formed by revolving that region R about the x-axis. So in this case, we are going to have our little region R, and if we're going about the x-axis, and we look at that little rectangle and spin that around the x-axis and then pull it out and lay it down, it's going to be a disk. So our delta volume is going to be a pi r squared h, and in our case that radius is going to be our function, so that's going to be the cosine function, and the height of that disk is going to be delta x. So our volume will become pi. We're going to integrate again from 0 to pi over 2 of, and that's going to be cosine squared x dx, and we're just setting up the integral expression, and so that's going to be the end of the story. And if we revolve it around the y-axis, then if we spin that thing around there, what we're going to get is a shell. It's going to look something like that, really thin. So in this case, our delta volume is going to be 2 pi r h, and we still have a delta x. So we'll go 2 pi r radius, that distance that goes from the axis of revolution out to our rectangle, is going to be just an x. And our height is going to be the function. That's going to be the cosine of x. And then we'll have our delta x is that thickness of the shell. So our volume is going to be 2 pi, integral again, 0 to pi over 2 of x cosine x dx. And if we revolve it around the line y equals -2, then we're going to have our region, and this is our x-axis, and that's our y-axis, and we're going to come down to y equals -2. So our little differential rectangle, when we spin it around there and pull it out, is going to be a washer. And so our delta volume for a washer is going to be pi, and then outside radius squared minus inside radius squared, and that's going to be a delta x for the thickness of that washer. So our outside radius is going to go from the axis of revolution out to the outer edge of our rectangle. So we're going to call that top minus bottom. So the top is just our curve. So that's going to be, we got pi, and then our outside radius is going to be that cosine of x, and then minus the bottom is going to be minus a -2. We'll make that a +2 squared. And then we'll subtract from that distance from the edge of the hole to that axis of revolution. And so that's going to be 0 minus -2, which is going to be just 2 squared, and then we'll have a delta x. So that will make the volume be pi, integral from 0 to pi over 2 of cosine of x plus 2 quantity squared minus 4 dx. Okay, if we revolve this about the line y equals 5, or x equals 5 rather, so here's our x equals 5, here is our little region, And if we take our rectangle and revolve it about that line, we're going to get a shell. So our delta volume for a shell is going to be 2 pi r h, and we still have a delta x for the thickness of that shell. So the radius here is going to be that distance from the axis of revolution out to the edge of our shell. And so we'll go right minus left, so that's going to be 5 minus, and that distance there is x, so that is going to make our radius be a 5 minus x. The height is going to be our function, cosine x, and we'll have delta x. So the volume is going to be 2 pi, integral again from 0 to pi over 2, and this time we'll have 5 minus x times cosine x dx. And the next one, we're going to take cross sections perpendicular to the x-axis that are equilateral triangles. So we're going to take a little section right here, and we're going to get an equilateral triangle. So I'm going to redraw that over here. Here's our equilateral triangle. Our delta volume is going to be the area of that cross-sectional piece times a delta x. And the area of that cross-sectional piece is going to be a 1/2 base times height because it's a triangle. This base across here is just our function. If we drop in the perpendicular, that height, that divides this into a 30, 60, 90 triangle. And so this length right here is what we usually call x, and the hypotenuse is 2x, and our height is going to be that x squared to 3. So that height is going to be, the x is going to be half of the cosine, so it's going to be 1/2 cosine x times the square root of 3, or more simply, square root of 3 over 2 times cosine x. So that makes our delta volume the 1/2 from the area of the triangle formula times the base, which is cosine x, times the height, which we said was square root of 3 over 2 cosine x, and then delta x for the thickness. So that makes our volume, if we combine these constants, that will be a square root of 3 over 4, integral going from 0 to pi over 2 of cosine squared x dx. Okay, let's see if we can find the centroid of that region R. Remember, our region looks something like that, and we've got this y-axis and x-axis. So if we look at a kind of representative rectangle, we're going to need to figure out what is the mass, what is the moment about the y-axis, what is the moment about the x-axis, so that we can get the x-bar, the x-coordinate of the center of mass or centroid, is going to be the moment about the y-axis over the mass, and the y-bar will be the moment about the x-axis over the mass. So the mass is really going to be just whatever the density is times that area. So our delta mass is going to be our delta area times, we'll just call it rho. And so our delta area is going to be just that area of a rectangle, which is going to be our function times delta x. So our mass is going to be rho times that integral from 0 to pi over 2 of cosine x dx. And I don't think I think we'll just use our calculator here. We can do this one, I guess, but I don't want to get buried in these integrals. So the integral of cosine is going to be sine x, and we're going from 0 to pi over 2, so that's pretty nice. It's going to be the sine of pi over 2 minus the sine of 0, and that's going to be just rho times 1 minus 0, so that's going to be just rho for the mass. Okay, the moment about the y-axis, we are going to take that distance. We're going to imagine our delta mass times that distance, and the distance to that rectangle, we're going to imagine that the mass of that rectangle is going to be just at a single point right in the middle of that rectangle, which we can think of as being a distance of x from the y-axis. And so that's one of those little masses, and we'll add all those up and it'll become an integral. And I forgot we need the rho in there. So, I guess our delta mass is going to be our rho times delta area, and then times x. And so that's going to be, again, rho times the cosine of x times delta x. There's our delta area. And then times x is the distance of that mass from the y-axis. So the moment about the y is going to be rho times that integral from 0 to pi over 2 of x cosine x dx. And that would be an integration by parts integral, which I don't want to bother with right now. So I'm going to pause this and just do it on our calculator. And I'm getting 0.571, so it's going to be a 0.571 rho. So let me remember these things so far. The moment about the x, we're now going to see that this is going to be our delta mass again, times, and now we want our distance from the x-axis, which we're thinking of as the midpoint of that rectangle, which is going to be the top curve, cosine x, plus the bottom curve, 0, divided by 2. So our mass is going to be rho times, and that's going to be cosine x times delta x, and then that's going to be times another cosine x over 2. So our moment about the y is going to be rho over 2 integral from 0 to pi over 2 of cosine squared x dx. And again, I'm going to just put that into my calculator. And I'm getting 0.393. So that means our x bar, the x-coordinate of our center of mass, is going to be the moment about the y divided by the sum of those masses. And since the sum of our masses is just rho, that's going to be just 0.393. And the y bar is going to be the moment about the x over the sum of the masses. And that's going to be just, whoops, I got that wrong. The moment about the y was the 0.571. And the moment about the x was the 0.393. So it'll be a 0.393 and 0.571 is our centroid, center of mass. Okay, very good.